Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 12. Students, welcome you all. And in this lecture, basically, we are going analysis and design of beams. Student, basically, this is a part of lecture 1, 2, 3, basically, okay? As we did basically some examples of beam design, okay? So you see here, determine the lightest W10 section suitable for the beam shown in figure, and we did this question number 1. Basically, our present lecture is basically related, or you can say the part of this 2-3 questions, okay? Basically we covered here. So I just recall your memories in this lecture number 12, because students asking for these lectures, sir, please do some examples on relevant to these questions. So that's why I am repeating the things in a very quick manner, and you just for the purpose to basically build your concept and wider your ideas, okay, relating to the design and analysis of a beam. Okay, so let's start. Basically I have to cover some examples from this Roland book. Okay, there are some interesting examples and a very good and nice easy approach. So here we have a steel beam design. Okay, let's start. We have basically, if I just recall your ideas, that we have a limit states, okay, and I discussed these limit states in lecture number 1 with some types of videos. Let me show you some videos which are relating with that. Okay, you see here that a beam is basically subjected, that is in intermediate length. Okay, once the load is applying on it, let's see. So you see, once the load is applied, you see the yielding of the girder, okay, because this is called bending or yielding. You can say the beam is basically failed due to yielding, or you can say bending. Now this is for an intermediate case, okay. Once basically, and this kind of beam, you see, look, this is a kind of vertical deflection, you can say, or bending or yielding. Clear? This is called yielding limit state. Clear? We have to check some other criteria as well, but let me show you some other. Okay, I also discuss on this video, okay, in my lecture number 3. Okay, here you see the beams flanges are basically buckled. You see the web is basically buckled, so this is how we call local buckling. Clear? Similarly here you see, clear, there you see that how the column flanges are buckled. This is called local buckling of the flanges. You see the flanges are buckled. So this is a kind of basically local failure. Okay, a web is buckled or yield, or you can say flanges are buckled. Okay, and here you see basically in this video a very interesting information. This is basically not a beam, this is basically a flat girder. Okay, remember that because in flat girder we are providing stiffeners, and I will do recording lectures relevant to the design and analysis of this flat girder. Inshallah they will be available on my channel, okay, as well. So you see here the loads are applied at this point and this point. Okay, and basically loads are there. Okay, loads are basically applied at these points. Why not it works? Okay, loads are basically applied through these points, okay, in this downward direction here. Okay, and these are basically providing a lateral stability or lateral. Okay, so Here you see basically, let me show you. You see this region, clear that in this region basically a local flange buckling is basically occurred, okay, and similarly followed by the web buckling as well, you see, okay. Let me show you. Once the load is increasing, okay, you see this kind of buckling which occurred in the flange. So this is called local flange buckling. And similarly you see here basically the web is basically start buckling, okay. So that is basically very important, which mostly occurred in plate girders, not just in roll shape beam, because they are compact. So this is how I want to show you that what these limit states are. Basically we, as you see here, that yielding I will show you in videos. Lateral torsional buckling I will also show you inshallah in my coming part, okay. And flange local buckling basically I already show you. Web local buckling I will also show you in basically in that video, okay. And what we have next, tension flange yielding. Basically we don't study this, or we don't do check for this tension flange yielding and for compression flange buckling or yielding something, okay. These are the checks basically which is used in plate girders, okay. Local leg buckling as well as in, I think so, in channel shape and angle shape, basically this matter. And local bucklings, okay. And shear checking, basically the web, okay, shear yielding, shear buckling. We will deal these topics in inshallah in plate girder analysis and design, okay. So let's start. What are the requirements? I already explained these limitation in my lecture number 1. Here we have some serviceability criteria. This is also very important criteria, okay, because if sometime a structure may in good position, you can see they are performing their function, but they do not remain unserviceable, or you can say the for the function which we basically design, like excessive deflection, a structure carrying its load, but if you calculate the deflection of that structure, that is without, you can say they are beyond the limitations, okay, or the limits. So these are the limits basically which we check a structure, okay, as we did basically examples of, and we see basically in basically composite section design in lecture number 9 and 10 we use these limitations. So for plaster ceiling we use this, non-plastering we use this, supporting ceilings, and for floor, look, for roof there are different limitations, for floor there are different limitations, clear. Similarly lateral torsional buckling, okay, we did I basically did example lecture number 8 and 10 on calculation of this CB, that is, you see here the beam bending coefficient or lateral torsional buckling coefficient, clear. And for different cases I explained these graphs or these tables in my lecture number 8. Now flexion requirement, I basically spend most of the time by discussion on this graph, okay, in my lecture number 1 to 5, 6 roundabout. We have 3 distinct zones, okay. We have zone 1, we have zone 2, we have zone 3. And zone 1 basically we try our best to design the section in this zone, because here you see the maximum capacity a beam can attain, like you can say the plastic movement, okay, that is the maximum movement. Then zone 2, that is inelastic zone, and zone 3, that is elastic zone. So for different zones we have different approaches. We calculate the moment capacity in this zone, the most simple equation, by so most simple. There is a little bit difficult equation we have to use. So let's see what coming in. You must remember what is LP, that is the limiting length for zone 1. After beyond, if your calculated length, that is unbraced length LB is less than LP, so you are in zone 1. And there we have just only checking the yielding. Remember, We don't need to check lateral torsional buckling, flange local buckling, because here in the first video you see the beam bends. So in that case there are no lateral torsional buckling, local buckling and something like that. Clear? In zone 2 basically we have to check lateral torsional buckling as well as yielding. Remember, while we coming in zone 3 basically we have to check local flange buckling or local buckling, you can say lateral torsional buckling and yielding. Clear? But yielding in these two zones, you can say they are optional, they are not occurred basically. Here lateral torsional buckling and local buckling basically control the section. Clear? But in this zone 1 yielding control the section, not the other two criteria. Clear? So let me show you zone 1. In zone 1 the condition is that your unbraced length should be less than or equal to LP. Clear? And your strength, basically we discussed this equation, Fyz times x, or you can say plastic section modulus, and Fy is the yielding stress. Clear? And the factor is 0.90. you have just need to calculate your Z required as I did my question number 1, and then you choose from table your required section, and then you again check it for the movements. Okay, so let's start this example, a simple example just like I did in my here. Okay, a simple example. So the UDL is the span is 30 feet and live load, dead load. So I think if you watch lecture number 1, so you got the answer of this, because both questions are similar. Okay, here 20 feet, there 30 feet, and only the loads are different. Okay, so the data is that you see Fy is this one, Fu is this one. Clear? You have to just check, select the most economical beam that complies with the deflection criteria. Remember, I think so in this question we didn't check the section for deflection, but here we have to check the section for deflection criteria. Deflection is basically, you say that it is a very predominant in designing such steel beams, because sometimes the beam plastic movement is developed, sometimes your section is able to take the acting loading, but sometimes basically once you design the section, although they will they're perfect, or you can say they can take the acting load, the movement factor movement, but they fail in deflection, there are excessive deflection. So that's why basically we check the section for deflection as well. So here you see we calculate the factor load, then we calculate the factor moment, and next basically they're going toward the checking of the section for deflection, and these are the IBC limitation, that is L by 360, and as you see previously International Building Code. Okay, so delta L, remember there is live load deflection, dead load deflection, and the combined deflection, that is basically dead load plus live load. So we check dead load deflection, live load deflection, and then combine them. Okay, and we basically find out which deflection criteria basically govern. Okay, so this is live load deflection. We have 30 feet span to convert in inches, because this formula works in inches, so you see 1.00 inches. Now this is the limitation. Remember, if you have to select your section on the basis of you can say on deflection criteria, you must use the deflection criteria in first, because if you watch this video in which I cover this example, I don't use that approach. Why? Because we don't need to check for deflection. Okay, if you are going to basically to select the section on the basis of deflection, you must start from deflection. Okay, because the beam, I already mentioned you that the beam is well and good for taking that the acting loading, but sometimes they fail in deflection check. So that's why if we do check in advance for deflection, so I think the section will be automatically fit for your acting loading. Okay, so that's why basically they start deflection for live load, they calculate this one. Now we already know this equation, and I already explained this in, I think so, in lecture number 9, sorry, in lower bound moment, when I calculating moment of inertia for a section. That remember, this formula is basically not in this shape. This formula is basically you have deflection equals to, and remember this is for simply supported beam. Okay, now you have basically W times L की power 4 divided by 384 times E times I. I is here, remember. Deflection is there, I is here. If you want that your section will be fit for taking deflection, or if you are, you can say, imposing a deflection limitation, that my deflection should not be more than this much. Okay, like here we got 1 inch. So if you want that your deflection should not be more than 1 inch, then we need to bring this Ix here and deflection here to calculate basically our Ix, and then select the section on the basis of your Ix, not by Zx. Almost if you visit basically my lecture number 1, here I basically calculate Zx. Okay, I calculate Zx and I select the section on the basis of Zx. But here the approach is different. We have to check, we have to require to calculate the moment of inertia and then select the section on the basis of moment of inertia. So that's why basically you see here 439.941 Q power 4 inch. This is the required moment of inertia for live load deflection. Now they basically did the calculation for total deflection. Now for total deflection, delta T is equals to L by 240. These are the IBC limitations. Clear? You just need to plug the values. You got the delta T and you see delta T is more than delta L. Okay. Now you see I required for this amount of delta T, you see that is 418. Now this is important. You see, for very important information. Okay, here your deflection is minimum, okay, 1 inch, but here your deflection is maximum. So that's why basically if your deflection is maximum, your I required will be minimum, or if your deflection is minimum, your I required will be maximum. Clear? So you must differentiate things. Okay, therefore I required is governed by the live load deflection. Remember, by the live load deflection. Okay, not by the total deflection. And the minimum moment of inertia is 440. They're just round thing. Okay, now because the beam is laterally supported for its full length, the unbraced length, actually it was, the beam is fully, remember, the beam is, you can see here, laterally supported for its entire length. This sentence is very important. Okay, because this sentence put you in zones where you are, zone 1, zone 2, zone 3. So as the beam is entirely basically supported, so that's why LB equals to 0. We all know, and I discussed it in lecture number 1 too. Okay, so that's why basically you see here, as the beam is simply supported and it's subjected to, okay, and the beam is totally laterally supported. Okay, so your unbraced length will be 0 feet and the full plastic moment MP will be obtained. Therefore CB is 1.0 and the beam is in the plastic range. Because remember, once the beam is LB equals to 0, remember this point is very important. I want to show you, if your LB, remember, less than or equals to LP, remember your CB will be, remember, it must be equals to 1. Remember why? Because this limitation when exists, this means the section is basically, or the beam basically in zone 1, and in zone 1 basically we use CB equals to 1. Remember, we don't modify the moment. Okay, now next you see your MU is less than or equals to 5B, because these are the LRFD are the code criteria that your acting moment should be less than your design moment, and your design moment equals to pi b f1 into zx. This is the equation which already we know it. Now z required, what modulus, section modulus, okay, plastic section modulus, sorry, you required. So you calculate that zx. Now we did this calculation in this example, clear, in question number 1, 2. You calculate your required zx. Now you need to choose your section. So the selection of the section is very simple. You just need to go to your manual, find the ZX table, and basically you have to go to table 32, okay, in manual. I think so this is 14 edition of AISC, not this one, okay. In this one basically the section is the ZX table. So basically students, this is our ZX table, okay. These chapter number 4, okay. You need to write down these sections, these chapters on a page, because then the searching will be easy for you, okay. So our required ZX value is basically 44. Now we have to select a section which ZX will be more or equals to round about a little bit more than this one, okay. So here you see the section and here you see the ZX values. So let us search it for this one, 44.2, okay, which is very close to 44.40. so that's why they select a larger section, clear. They select a little bit larger section and they select this one, clear, with a 47.3, clear. So yes, okay, we select 1430. The ZX is 47.3, which is more than 44, okay. We can't select, sorry, that section, that W1426, this is less than that one, okay. So ZX, you got your ZX. Now you need to recalculate your moment capacity. You just need to plug values here. Your ZX now 47.3, plug here and just calculate the design capacity and compare that capacity with MU. So you see your design capacity right now 177 feet cap, which is greater than this one, okay. And your IX for this section is basically what? Your I section for this IX, now you have to go back to the actual section, okay, right here, where this right W section, clear, this one. And here you have to scroll down and find that section, that is W1430, this one. And here you have to scroll down and 1430 have a YX is what have they selected? IX291. So IX291 you see right here, this one, clear. So this is your required 291, okay. This is your required value of IX, which is more than the required value, okay. Because you see where we are 510, what it is, our section was IX 510, where the section is W1430 section, this one, okay. Its IX is basically 291, okay. Yes, 291, and here, yes, 291, sorry, I was looking to this one. There you see 291, which is less than 440. So that's thing, that is which I want to share with you, okay. That sometime you design the section, although your section is okay, their capacity is more than the acting factored moment, but here the section failed in deflection criteria. So if you select the section on the basis of your deflection criteria, I think so that also work out for definitely work for your factor moment. So that's why they revise the procedure, and they basically go to the IX table and they select a section that's is now a bigger section and a heavy section as compared to the previous one. And you see they select a section 1835, but on the basis of moment of inertia, not on the basis of ZX. So that is the key purpose of this lecture, that you have to select then your section on the basis of moment of inertia. Now once they select the section, they find out the ZX of this section from the same table which I have, this one, okay, and then they insert the value. You see here the difference. Look, here the ZX is 66, which is more than required value of ZX. Okay, the capacity is more than, and that's my key purpose, that if you select your section on the basis of your IX, or you can say from your deflection criteria, then it will definitely work for your moment capacity. Clear? But if you select your section on the basis of your ZX table, it may sometimes fail in deflection criteria, as you see here, but it is not necessary. It may sometimes pass, but here you see it has failed. Almost you can say they failed. So that's why we have to select, and the IX which is calculated is 510, which is more than 414. Now the section is okay. So this is the key purpose of this lecture, that how you can design basically a section on the basis of IX, not on the basis of ZX. Clear? As we did basically in this example, if you watch this lecture, that is lecture number one basically in my steel structure course. Okay, so you see I select the section on the basis of ZX, but I don't check the deflection. If you people do check for the deflection, you see this section which I select in this question will fail. Okay, please do an exercise on it. Okay, so let's moving forward. I think so this will be enough. Please share your question and watch the video and enjoy. See you in next lecture. Thank you.